Welcome to Computability Freaks. I'm your host, Aaron Carmody. You might know me as the star of the hit TV show, Computability Freaks. Why don't you come with me on this journey through Soare's The Art of Turing Computability, Theory and Applications. Today's episode is the basic results. Welcome, everyone. Hello, freaks. So today is Monday. We had a big snowstorm and lost all power. So yesterday was kind of a dud. It was kind of fun though. I read some books. I read a book called The Whole Cat and Caboodle. All the details are just about the cat doing stuff. It's great. But anyway, so I like to do Computability Freaks on Sunday, every other Sunday morning. But okay, so it's Monday morning now. So I hope you're here. Oh, okay, so I wrote some things out for myself. I kind of wrote some of this stuff earlier, so I might forget. But I wrote this you get things in your head and you have to keep repeating them. So I just wrote down. Okay, this is a disclaimer about this show, and that's that I am going through this book for the first time, and so it's kind of a read along versus a lesson, because when I do this, it's really helpful to me to read the book, and hopefully for you too if you're reading the book, and then afterwards I watch it, make sure it's nothing terrible, and that's helpful to me. I'm like, oh, I kind of then the ideas kind of click in place. So it might be frustrating if you're trying to learn computability from this. It's kind of in somewhere in between like a read along and a lesson. I mean, I don't want to be inaccurate because that's not fun either. But so you're like, what's the intention of the show? Okay, first it was a revenge plot because I tried out for a play and I didn't get it, and so I made the Computability Freak so I could be the star of my own show. But then I ran out, ironically, after I made this show, I did get a part of in this play. And then I had to cancel it. I couldn't do it because I couldn't do it along with everything I was doing this semester. Okay. But I would like to actually get involved in that somehow. But okay, but then so also I wrote my paper on NITT, a non-deterministic infinite time Turing machine that I submitted to something. And I might have to give a talk on this. So I just like to be more familiar. I'm not so familiar with computability, so that's why we're here. I was also I just want to talk about just what do you create? Why do you create it? And why do you do what you do? Why do this? It's and I think there's just something that I was thinking about was that this is related to math as well. I'll just give an example of math. Someone, a mathematician once told me, not John again, that maybe you should do more work that's applications. Okay, now they're not getting crazy. You're not talking about applications of physics, but applications of set theory to other areas of math. And so I was I would love to do that. I would love to be able to just focus my attention on whatever I think is important and work on that. And I just don't think it works that way. In my experience, it doesn't work that way. It's okay, God gives me, I'm using it as God gives me something. Here's an idea. Here you go. And so I can either take it or not. So if I don't take it, it just that nothing happens then for me. I don't get any other ideas after that, unless I finish the other idea I already had. I was just sit there. I feel like that about art too. It's I just have to create and put it out there. I can't judge it too much. I can't. I was watching Andy Warhol interview, and he was saying, someone was like, "What are you?" I loved his attitude. Someone's like, what do you think of your own art or something? And he's like, it's not for me to decide. I just have to create, put it out there, let them decide, keep creating. I feel the same way. It's almost like I wish that I could be okay, I'm going to use my talent to create something in this specific thing, but I can't really do that in my experience. It's if I have some idea, if some idea pops in my head, I have to do that idea. It's that's also a balance of impulsivity too a little bit, but this is a creation that takes a little while, but okay. So I just wanted to talk about that. Do you feel the same way about math? Can you decide, okay, I'm going to work on, let's see, applications of set theory to algebraic geometry or something? No, I don't know. Do you feel like that? Or for me, it's just I have one idea, with this NITTM's paper, which I didn't do anything with for a long time, and then I'll use this as an excuse. Then God's like, well, you're not going to get anything else, so you might as well just do that one, and it's okay. There was another thought with that though. It's God's not gonna give you another one. I can't remember. Okay. Okay. Oh, I see. Yeah, the thing is that sometimes I don't want to okay, this is again my excuse, but I don't want to publish something, or like if I have some idea to write it up and do it, because then I'm like, well, what am I going to do after that? Sometimes with art too, I'll have an idea of something and I'm like, yeah, but what am I going to do after that? Once I do that, what am I going to do after that? But I've learned that like, just do the thing. Maybe you'll get some idea. I still haven't like exactly had this yet, but like, maybe some idea will come later from what you create. Maybe you put a math idea out there and then someone says something and inspires the next idea. Okay. I just have to create. Okay. I don't know how you feel about that. Yeah. Well, it's not like I can just say, oh, I'll just work on this or I'll just do this. That's just how I feel. But also in this thing right here, I probably would talk in a way that I wouldn't talk about as like teaching a class. When I'm teaching a class, it's much more like I'm actually pretty nervous, so I don't really say that much. But no, I'm an excellent teacher for anyone. No, I know it's fine. So yeah, I think it's a little bit more like less of a lesson and more like something I have to do, a creative project, and also we'll be learning about computability, and it helps me quite a lot. Okay, so sorry if I make a lot of mistakes and stuff. And okay, also as far as the recording goes, I was able to get my iPad can share now, so we're gonna try this. I think it's better so you can see the notes like a lot better. Okay, so we'll see if I can share this. Okay. So sorry if I'm like blowing my nose and stuff, but okay. So let me see if I can get this. Okay, now how? Okay, so let's see. Excuse me, I just have to. This is probably gonna be. I'm sorry. Okay, we're gonna get to some stuff. I'm so sorry. Please edit that out. I don't know how to edit videos. Okay. Okay, so I'm going to share my screen. Okay. Okay, so let's go through this. I like a, okay. So I don't know if you did the homework, which was we were just finding a Turing program for adding, no, for doubling for just 2x. So we're trying to find a machine for 2x. I'm not going to go through this though. I think this works. I don't know. I mean, you should do it yourself. But the idea is that the extra input, because you know how if you input of 2, there's 3 ones there. So I hope it's okay. So I don't know, I got rid of one of the ones, and then okay, I go here, I have something that goes here. It skips over the blank or the 0, and then writes 2 ones for this one. It actually makes this a 0, so you know you've already been there. And then takes this, comes back and gets this one, ferries it out there, and then takes this one, makes it a 0, and then goes out when there's a space and writes 2 ones. Okay, that's the idea that I think is the general idea. I'm sure you can look it up. The other one we were doing, f of x is 0. Yeah, just keep writing 0 when you're in state, the Q1 state. Just keep writing 0. I keep writing zeros, covering all the ones until you get to a blank and go into halting state. Okay, I'm using zeros for blanks. But yeah, x plus y was really hard. I mean, x plus y is easier, a lot easier, because the input is a pair, so you can just leave them basically. I mean, maybe there's an extra 1 there you can erase, but you can just leave them basically. And adding, wait, so we did that one, we were doing +3. We were doing, and then I was doing, so we did +3, and then I did +4, +5, up to +x, but then the program has to know what x is to write the program. So that didn't seem to work. So then I had to do something else. Okay, it was, it's hard. That one was hard. Like the 2x, I spent too much time on. I don't even know if I got it right, but okay. So we are in basic results. We have some interesting results today. I think we do the padding lemma and the universal machine lemma today. I might not go through all of 1.5. And again, my goal, I think this semester, I think we will do this, even though it doesn't seem like a lot, is just get through through chapter. I'm sorry. Okay, through. Through chapter 1, yeah, we're gonna get through chapter 1. I know it doesn't seem like a lot, but what's the rush, what's the rush? Okay, so for this section, we're gonna need Gödel coding. So we can take this list of natural numbers or the set of natural numbers, and we take the primes and then you use these natural numbers as exponents, and now you've coded this quadruple as a number, and it's unique because of unique factorization by primes and powers of primes. Okay, another thing we can do is the pairing function, where it's this pairing function. I don't know who did that. It's one-to-one, it's computable, and it's a one-to-one computable function from omega cross omega to omega. So you've got a pair you can code with a one number, and then I think if you have a triple, you can like code the pair first and then code the next pair. It's like that. Okay, so we're gonna need some kind of like Gödel coding. We'll just use Gödel coding, I think. Okay. Oh, and today we have like some other fun stuff too, by the way. We're gonna do this and then we have some other fun stuff too. It's all fun, probably, right? Okay, so the first thing is about numbering of Turing programs, P sub E. Okay, so each Turing program we know is really just a collection of quintuplets, or you can think of that like, like pair to a triple. So each Turing program is a finite set of quintuples. We can just list all the Turing programs in such a way that for any program, we can effectively find its number on the list, and conversely. So here's just to imagine, I have our Turing quints, this program P sub E. We can code this program with a number, and we can then we can number all the programs and put them on a list. Okay, so let P sub E be the Turing program with code number E, index, we could also call index E. Let's phi sub E, so the capital P's program, phi sub E, or should we say var phi? I think we should say var phi because we're going to see a phi. So the var phi sub E to the n in parentheses be the partial function of n variables computed by P sub E. If there's no exponent, it's just we assume one variable. And var phi sub E is a partial computable function. They're both identified. So here's P sub E and phi sub E, the program and the function. And they both are identified with the program P sub E. And this is a what's that? Partial computable function. Okay. This is the standard numbering or canonical numbering of Turing programs and partial computable functions. Okay, so we're gonna see, I guess, what do we see later? Like, we actually see the function, the computable function that lists the Turing programs. Okay. 1.5.2, the padding lemma. And this says that each partial computable function has var phi sub x, partial computable function var phi sub x has infinitely many indices. Okay. Furthermore, for each x, we can effectively find an infinite set a sub x of indices for the same partial function. Okay. Okay, so consider var phi sub x and the associated Turing machine P sub x. P sub x is a bunch of instructions, like a bunch of quintuplets. And so we can just modify that. And let's say it has these states Q0 through Qn. We can modify that to just add some states that don't do anything. So I'm going to add Qn plus 1 on a blank. It does this other stuff. But the program will never go into that because it doesn't have a... If it couldn't get there before, it's not going to get there now. So okay, so we add some new states. Okay, so then we can get a new program for the same function. Okay, and then those are going to be have a new code with the extra instructions. You're going to add a unique code. Okay. Okay, so that's the padding lemma. Okay, so we can say that for every the var fees when we see this is for computable function. So when we see it has some index e, we know that it's also that this computable function can be computed by a Turing program p sub e, but it can also be but it can also be but it also can be computed by p sub some other e prime that also that is like p sub e, but it has more instructions that we don't need. Okay. So the padding lemma. So there's lots of different, I guess there's lots of different names for the same like computable function. Okay. 1.52 numbering Turing computed computations. Okay, I'm gonna have to look. I think I left some of this. Okay. We say M can okay, okay. 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 Let's just see. Okay. As soon as M, okay. As soon as M reaches a stage V of a configuration which contains the halting state. So it reaches a halting state. I feel like I'm being wrong about this. Okay, so I believe for converges it has to go into the halting state. It outputs some ones. Never enters another configuration, turns off, never enters another configuration. So then it converges. But there's lots of things that can do for diverging. It could go on forever. It could enter infinitely many different configurations. Or go in an infinite loop. Okay, one time I did a art piece, which was when I first learned about computer programming, which was like it was like an infinite loop. Like it was just written. It was just like it would look like slate and then white on top, and it was just like an infinite loop. And I don't remember what the loop actually did, but it was something about that Blue Oyster Cult song about 40,000 men and women every day redefine happiness. It was about that. I don't know, but that was a piece when I was an undergrad. How did I don't remember learning about programming, but I must have. Okay. All right. Okay, so for it goes in an infinite loop, infinitely often, or stall at some configurations. Okay, so any of these things are diverging. Okay, now infinite time Turing machines, there's a little more. Okay. What are we doing here? We're talking just what's M. This is just definition. What's diverging, what's converging. Oh, this is also about coding the configuration. Now, okay, I think I wrote down this. Okay. So assign numbers. So I think it's okay. Assign numbers to each tape symbol SI. So you can also code the entire configuration. What's everything written on the tape? What the state is. So we can assign configuration C to using good coding. But I think maybe the point is that you can't necessarily do it if it's a not convergent. Okay. I think that's all. That section I felt like I just needed to read every sentence very carefully, but I felt like I didn't quite. I think the point of that was just that you can code the configurations, computations. Computation is like the collection of configurations. Okay. Theorem 1.5.3. I'm going to write this down because I just thought that this theorem, if you just read it, you might be like, what? They didn't do any. I don't think you did anything, but it's just, so let's just take it. I'm just going to write every word so that we see it. Okay. Okay. Now, I also want to point out, like before this, he's talking about, Soare's talking about, we saw there's no effective numeration of all total computable functions. However, effective numbering in the preceding subsections for the syntax of Turing machines allow us to now give an effective numeration of all partial computable functions. Okay, and I was thinking about this. I'm like, okay, the total computable functions are a subset of the partial computable functions, but somehow the totals aren't computable. But they're somehow on the list of all the Turing machines, all the programs. So that seems kind of weird, but I guess it's like, yeah, they're on the list, but it's not go and find and list all the total computable functions, because we'll run into that contradiction again. We'll just define, let's say G is the computable function that lists all the total computable functions. We'll write H is a G of XX plus 1. Okay, and it can't be equal to any of the total computable functions. Okay, so that's that. Okay, so let's just write, this is called the enumeration theorem. And universal machine. Okay. Just looking at how bad my handwriting is. It's because I'm writing this weird way up here. Okay. Okay. Here we go. So let's write it out. So there is a partial computable function, PC, of two variables, phi ex, such that phi ex equals var phi sub e of x. Oh, it's packed in that sentence, because it's like, what are you even talking about? Like, but we have to remember that var phi means a computable function. So this is saying that there's a function, a computable function, such that given any Turing program E on input X, you can like simulate the program. So like, this is saying like, yeah, so if I want to compute, what does program E think about when I have input X? What's the output? I could just ask this function phi, put in EX, and then it'll give me the output Y that var phi sub E would have given me on input X. Okay, so there's that. And then the second sentence is that by TT, there is some I such that there's phi sub I EX equals phi EX. Okay, now think about how we didn't know what TT was. I just love thinking about alternate histories that are. So if we didn't know what TT was, we'd be like, wait, does that stand for Turing thesis or Turing theory? What is that? Oh, but we're good. We know what that means. So by TT, so by Turing's thesis, there is some I such that phi sub I of EX equals, so that there's a computable function, no, that there's a Turing program, there's a computable function, there's a computable function, phi, their phi is a computable function. I'm so sorry. I get this in my head and then I'm like, and then all of a sudden it doesn't make sense to me. Okay, we know that okay, phi sub I is a partial computable function. But we already know that phi is a. I'm sorry, guys. I was gonna have this big moment where I was like, we know that this means. That's why I wrote it here, because I did. Okay, but by TT, there's some I. So Turing's thesis says that the the our idea of a human being doing a computing is the same idea as the Turing machine. Okay, let's just go back to it. Okay, TT is the Turing's thesis. A function is effectively calculable by a human being if it is only if it can be computed by a Turing machine. Oh, okay. So oh, okay. A function is effectively calculable by a human being if and only if it can be computed by a Turing machine. Okay, so we have this. Okay, let's just go back again. We have this var phi. It's a computable function. So it can be computed by a Turing machine. Now, phi sub e's are the computable programs, but we're kind of like identifying the program and the computable function. Okay, so let me just say what I think this last sentence means. So by TT, there is some I such that var phi sub I of EX equals phi of EX. Oh, that there's a Turing program that oh, okay. So okay. Let's keep talking because I'm getting myself stuck in a loop. Speaking of loops. Okay. But I don't want it to be like, because I know I'll watch it back and be like, this is so annoying. But okay. So so we have this like computable function. So okay, so we have this computable function. Okay, we have this computable function, var phi, that can like simulate any Turing program on input E. I mean on input X, Turing program E to input X. By TT, this phi here can be computed by a Turing machine. So that's what they're saying. There's one machine. Okay. So we have this computable function, a function of two variables that can like simulate a Turing machine on some input X. And then we'll say, okay, not only that, but we have a Turing machine that computes phi. Okay. Okay, so we're just trying to see now, how do we, okay. Sorry, I wrote all these notes. I'm trying to like tell myself. Each Turing program piece of E is coded by E. Each computable function. Oh, I'm just rewriting. Okay, I'm just rewriting some ideas there. Okay. Okay, so let's just go through this proof here. So MEX, so the Turing program which computes this amazing phi EX is a universal Turing machine. Okay, so you're given inputs E and X. So the first thing to do is E, we know that E is a code for a Turing program. So we're going to recover all the instructions. Okay, so how are we going to do that? So we have this, E is really, okay, so you've got these instructions. Let's just think about how E was made in the first place, and then we'll talk about how we can recover it. So I have a Turing program. I have all these instructions. Each quint becomes a number. We'll just use the prime powers one. And each of those can be coded, each of the quints can be coded by an ace of I. And then E will be 2 to the ace of 1, 3 to the ace of 2, 5 to the ace of 3. And this is unique factorization of E is colored. Okay, so let's say we're given E, so that's how it's created. So if we're given E, so we have to put E. Factor E to get the AIs. So we're going to factor E, get the AIs, factor the AIs to get the program instructions. So just work backwards from what we just did. Okay, so we're going to convert E into a Turing program piece of E. So we're going to recover all that information. Okay, and then we're going to first it's run. We're actually simulating program piece of E, which we've now recovered all the instructions for on input X. And we're not exactly letting it run because we're not just like, okay, go run. We're kind of like each step we're sort of manually taking the next step by looking at the program instructions. Okay. Oh, also I was going to mention a sequence of configurations. Or snapshots. Okay, so you can use snapshots. I asked Joe Hampkins that too. You can use snapshots. I kind of like snapshots, that word. And a sequence of configurations or snapshots is a computation. Okay, I didn't want to go into it too much, but it's like, it seems kind of weird because you're like thinking about this machine. I know it's supposed to, I think it's all happening simultaneously, but you do kind of think like, well, the head, there's like a point when it's like rewriting that one as a 0 or something, and then it's got to move. So if you were actually taking a movie of it, like you'd see these moments where it's like halfway between this spot and stuff. So it's like a discrete snapshot at certain moments or something. Okay. So suppose, so what are we doing here? Okay, so the simulation begins in state Q1, the leftmost symbol on X in standard input form. So suppose the simulation is in state QJ reading S sub K. So we have the instructions for piece of E. So we're going to manually look through and find some instruction like this, where it's state QJ reading SK, which is what we're doing right now. Okay, and it finds the first instruction of this form. with the QJSK there, and performs the action. So MEX computes phi EX. Okay, so again, just on input EX, convert E to a program P sub E. It's like sometimes I say things and it's like, I know I totally don't understand what I just said. It's really annoying. It's really annoying to watch and be like, okay, I'm trying. Okay, convert E to program P sub E. Simulate P sub E on input X. If P sub E on X returns Y, so does M. If P sub E never halts, neither does M. Is that it for, okay, the remark, I thought we'd just read the remark. Yeah, I think we just read the remark together. Okay, I'm sorry. It's like, okay, this is a non-alcoholic beer. Sorry, that's just what I have. I actually quit drinking like a year ago, but I like the non-alcoholic beers. Okay, so let's read this. The enumeration theorem is crucial for all our work. For example, to show that a set A is undecidable, we must show that the characteristic function of A is not equal to var phi sub E for all E. That requires effectively listing all algorithmic partial functions var phi sub E, E, and omega. I had a little comment on that question. In 1936, Turing approached this in machine fashion by explicitly specifying a universal machine, a single machine which can compute any computable sequences. Turing's universal machine took as input a number X in a Turing program, which our notation would be a finite sequence of 5 tuples for the Turing program, and his machine performed as in step 2 above. Okay, I guess I get a little confused when they say they say the set of all, listing all algorithmic partial functions, phi sub E, E, and omega. And it just seems to me like there's not going to be a Turing program with code 1 or 2 or 3 probably. I mean, it's not going to start, you're coding a lot of stuff. It's going to be a big number. But I don't know. I don't know if that's a thing or not. But that's something that gets me a little bit tripped up. Okay, so I don't know if we'll do this together or if we'll just go on to 1.6. I'm sure these are really important. The parameter theorem or SMN theorem. And unbounded search theorem. Okay, but I thought that's enough because I was already like losing my mind on that. Okay, so the thing that I thought would be fun today, so is there was a paper that I saw on Twitter. There's like a oops, did I do anything? There's like a paper. It was like the computer science like is it a bot? I don't know. I don't think so. One of those like I'm a computer science or whatever. It's a really great article. I thought it was like so much fun and it was like so much information. Okay, so let's just talk about P versus NP for a second because that's something that like I had the reason like over the break I was working really hard on this NITTM paper. I don't know why I said I'm working really hard, but it was effort. But I had to like write just a couple sentences about P versus NP. And I was just struggling so much, just taking like days to just think about what is P versus what does this mean? Because it's like it's not like a problem like Goldbach's conjecture or like the Collatz conjecture or something where you can just state it. To me, it's a very, very human oriented what do you call it? Conjecture? I don't know. It's so it took me a long time to even be able to talk about it, be able to have some kind of opinion on it or anything like that. And I still am like, I just feel very far away from that. I mean, and I'm thinking about like all these papers. What's that guy's name? Steven something. I forgot. There's like the guy that like created. Well, we can actually look on here. I don't want to like. Okay, so we can look on there. But so I'll just say like what like a very like analogy of what is P versus NP. Okay, and I'm gonna use an analogy here. Okay, I'm not trying to be like religious or anything, but I just use God a lot when I'm talking about like explaining how things work or something. It just okay. So this imagine this. Does any like okay? I'm just gonna say this way because I think it's even hard to say. But okay, so imagine God has these. God has all these. We're on a different kind of planet, and God has all these kind of creatures, and they love solving problems, and they're good at solving problems, and that's like what they do. And God's kind of experimenting around, and he's got his. They're like little programs, you know. They know what to do next, and they do the thing. They have like some intuition or something. Um, and so he's doing experiments. He's like, I'm gonna make my special children. Now, my special children, they're non-deterministic machines, meaning that on some input and being in some state, they can go into two states simultaneously or more. And I'm thinking about, so imagine you might maybe have the similar experience when you're having a conversation and someone's like, they say something and you're like, you instantly think of like a whole branch of things that could possibly said, or think there's so many things that could possibly be said right now that. And so as you're going through this list, this branching of possible conversation topics, by the time you're kind of like thinking of one that it's already moved on, and you're just standing there like. So okay, so you can imagine that feeling. Okay, not it being non-deterministic or something. Okay, so God's like, I want my children to solve problems. So he gives them all these problems. And the question is, in the end, they're all very good at solving problems, but in the end, there's some really hard problems. In the end, will the ND children be able to solve harder problems in the end? Can they actually solve harder problems or not? Or is it just that everybody, different strokes, but there's no like more strength in any one of them. Okay, but then there's this thing. So it's see, I don't even want to talk about it but like then there's like this polynomial time thing involved too. Like and for a long time I was like, why polynomial time? What does that have to do with anything? Like I don't understand. But I think it's a human thing. It's like that's like something running in polynomial time. And I believe that means that on input x, it takes some polynomial of x. If you plug x into a polynomial, that much time to solve. So it's like the relationship between the input and the time it takes to compute. Okay, the polynomial time. But it's like, what does that have to do with anything? Because I think it's human things. Okay, so that's my like very vague like what is P versus NP. But let's just read this article because it's just kind of fun. Okay, I'm sorry. Please don't see anything. Please don't see anything in there. Okay. Girl's last letter. Okay, so this is girl's last letter. P equals NP. Is P equals NP an ill-posed problem? Russell Impagliazzo is one of the most original thinkers in complexity theory and is famous for wonderful things. One of his papers is on many worlds. The worlds are algorithm, heuristics, Pesseland, mini-crypt, and cryptomania. Today I want to talk about a different take on P versus and the impossible worlds we live in. I'm not going to read this whole thing, but I just want you to. I just thought it was cool. Like they're talking about the Riemann hypothesis. The prime number theorem states that pi of x is the number of primes less than x, well approximated by this logarithmic integral, where the Riemann hypothesis, the error term is okay. Okay, well that's okay. And they said the failure of the Riemann hypothesis would create havoc in the distribution of prime numbers. Okay, then I'm not going to go through. It's like, okay, then they're just considering what would happen, and it's just if P equals NP, then they're okay. So you could have a really high exponent. Okay, I didn't like this one for some reason. The really high exponent. You win the. but it wouldn't have any practical impact. I don't know. I didn't like that one, that outcome. And it might just be like polynomial in a very weak sense. There might exist an algorithm that runs n to the c time for some constant c that is not even known. Oh, okay. I like that one. I like that one. If the proof, you just know that it is true, but you don't know what that c is. I kind of like that. Or maybe it's like independent or something. Like you could have different worlds or something. I don't know. And then if p is not equal to np, I don't know what he said. For every polynomial algorithm you have, I have an exponential algorithm that I would rather run. What if it's exponential, but it's like just slightly so 1.10000001 to the n. Okay, SAT might have wild complexity, perhaps. For some ends, the best running is exponential, but infinitely often the time is polynomial. I like that one. I don't know. Oh, I told you that, but in my paper we talk about an infinite time case. Okay. It's p is not equal to np. Ralph Schindler show. The Riemann hypothesis again. Okay. But I just like this because this is the scene I wanted to read. I just thought it was like super fun, just because they have this whole like dialogue going on. Okay. Okay, here's two scenarios. If p equals np and p is not equal np. Okay. George barges into Paula's office without knocking. She is about to complain that she's in a meeting with Ted when George says, she's complaining that she's in a meeting with Ted. What? And George says, oh, because he busted in. She's not complaining that she's in a meeting with him. She's complaining that the meeting got interrupted. Okay. When George says, Ted, did you hear p equals np has been proved? I just got off the phone with Lance and the proof is correct. Paula sees Ted jump up at this and says, are you kidding? Why didn't he tell Paula? Ted and Paula, did you hear? Sorry, George is out of breath but smiling. It's no joke. Unbelievable. All unbelievable is all that Ted could manage. Paula has never seen George this excited. It's really true that FOCS program committee accepted the paper even though she did not submit it. I guess that's a first. She just missed the deadline or something. Paula sits behind a large desk and is covered in books on circuit design, and VLSI says, this is great. Finally, you theory guys have done something that I can use. Oh, okay. I can't wait to get my team implementing the algorithm. She sees Ted sit down. He is turning pale and mutters to himself, damn it, this wipes out Fred's thesis. I told that idiot to finish it last spring. Paula ignores him. This will change VLSI design and testing. And George interrupts her. Well, not quite, Paul. I hear that the running time of her algorithm is bad. What? Like how bad? I think it's n to the 2 to the 2 to the 100. Although I forget if there's a logarithmic factor too. But p equals np. George barges into Paula's office without knocking. She's about to complain that she's in a meeting with Ted when George says, Ted, did you hear that p is not equal to np has been proved? I just got the phone with Lance and the proof is correct. Paula sees Ted jumping up at this and says, are you kidding? George is out of breath but smiling. It's no joke. Unbelievable. Unbelievable. See, the thing about this problem, though, is it would have impacts in the world. Like if I solve Goldbach's conjecture, I mean, I don't think it's going to impact any technology or anything. That again, this is big stuff here. Paula's never seen George this excited. No, it's really true. The STOC program committee accepted the paper even though she did not submit it. Oh wait, yeah. Paula, who's listening behind a large desk covered in books, circuit design and VLSI, idly checks her Seiko. It's almost 12. She needs to leave for a lunch meeting soon. Ted says, I knew it. That crazy blogger, what's his name, was always talking about P could equal NP. Well, he was wrong. What an idiot. George says, yeah. How does the proof go? It's a circuit lower bound. She proves SAT requires at least n to the log of n size circuits, avoids the usual roadblocks by using that new combinatorial lemma of Terry. Isn't it wonderful? Paula, who a moment ago was hardly listening, says, "Did I hear you right? That's not a very big bound. Let's see if n is a million. Let me see. That's not even quite. That's not even a quadratic lower bound. Were those logs base 2? Of course they're base 2. Logs are always base 2, but it's a super polynomial lower bound. P is not equal to NP. Okay." And then he says, "My apologies to all fiction writers that have ever lived." I just greatly enjoyed that. Okay, let's end the day. Don't please. Okay, don't look. Okay. Let's get back to this. Okay, so I just like to read Turing's. Okay, red, orange, yellow, green. We'll do blue. I didn't read this yet, so just do a tiny bit. Okay, let's get into Turing mode. Although the class of computable numbers is so great and in many ways similar to the class of real numbers, it is nevertheless innumerable. In section 8, I examine certain arguments which would seem to prove the contrary. By the correct application of one of these arguments, conclusions are reached which are superficially similar to those of Gödel. These results have valuable applications. In particular, it is shown that the Hilbertian Enden-Dunch problem can have no solution. Okay. Let's see what post. He writes so much. I'll just read a little bit, you guys. I love you, Post. I'm interested. Okay. A set of positive integers is said to be recursively enumerable if there's a recursive function f of x of one of the positive integral variable whose values for positive integral values of x constitute the given set. The sequence f of 1, f of 2, f of 3 is then said to be a recursive enumeration of the set. The corresponding intuitive concept is that of effectively enumerable set of positive integers. To prepare us in part for our intuitive approach, consider the following 3 examples of recursively enumerable sets of positive integers. 1 to the 2, 2 to the 2, 3 to the 2, 1, 2, 2 to the 1 plus 2, 2 to the 1 plus 2 plus 2 to the 1 plus 2, 1 to the 2, 2 to the 2, 3 to the 2, 1 to the 3, 2 to the 3. Let's continue that next time. I like to procrastinate. Well, that's all for today, folks. I hope you're having a great day, and we'll see you next time on Computability Freaks. We'll see you next time on Computability Freaks.